start by sharing my screen. So I hope you can all see my screen. Okay, well, it's a tremendous pleasure to be here and to be talking within the London Mathematical Society. Because it's more of a mathematical lecture, I'll try to highlight some of the beautiful mathematical and particularly analyticity requirements that we may actually be able to see in the sky. But first, let me follow up a little bit on the comments that were made earlier and have a special thank to the London Mathematical Society and also to Mary Cartwright. And perhaps following on what Eugenie mentioned earlier, I should probably say, and Anne was very humble there, that I probably wouldn't be here if it wasn't for Anne. And following my first year of PhD, anyone would have decided, including myself, that continuing into theoretical physics was certainly not for me, and my potential was probably better somewhere else. And I really owe Anne a lot, and probably everything. She took me under her wing and showed me that indeed there's a lot of diversity in the way people show their potential in the early years, and how important it is to appreciate. So thank you, Anne. I also thought it would be nice to start with one of the International Congress of the Mathematicians. This one is almost 100 years ago in Zurich in 1932. And it was remarkable, first of all, of course, because Mary Cartwright was there, present here. She was one of only 5 women presenting a talk during this event. And actually in 1932 was the first time a woman was ever invited to give a plenary talk. And that woman was no one other than Emmy Noether. So it is showing the lack of diversity at that point, but also it is a little sad that one had to wait 50 years until the next woman was invited for a plenary talk in International Congress, until the Kyoto Congress of 1990. So there's been remarkable development at every scientific and diversity level over the past century, although maybe it's fair to say that some of those developments could have gone a little bit faster than others. But to go back into the science side of things, and because I like my talk to be positive, let me just say there's been a century of progress in mathematics as well as in gravity. And this progress is supplemented by an incredible variety of tests from the point of view of general relativity, which has been tested on a multitude of scales, from sub-millimeter scales on Earth and throughout the solar system to cosmological scales. And of course, the recent direct detection of gravitational waves showing how dynamical gravity is, and the first pictures of a black hole shadow really are flourishing the theory of general relativity as the beautiful theory of gravity, or perhaps the unique theory of gravity we can imagine. However, at the core of all of this success, there's always a few shadows that, if we forget them, we may carry on with our lives happily, but they're still there. So it's been a century of success if we ignore a few of the elephants in the room. A few of them are, well, we have a beautiful description for our universe, but how did it start? We can't even describe the beginning of our universe, and we can't describe the future of our universe. So we are limited in the descriptions of gravity. And then a little bit more pragmatic, we know that the universe is filled with some dark components, dark matter and dark energy. And what we've been doing so far is describing them at the effective level, giving them some equation of state parameters, for instance. But these are just substitute for a better understanding of what these fundamental constituents are. And so a lot of what I'll be talking about today is really related to any of the open questions that we may have about gravity, about cosmology, even about particle physics, or about physics in general, about science in general. But to be concrete, at least at the beginning of this talk, I'll be focusing on the question of dark energy. And it's not because I'm particularly wedded to dark energy per se, but it's just an example where some of the strategy in exploring what dark energy is can be implemented particularly well. And then we can explore these lessons to other concepts that we want to study in science. So let me focus with the dark side of the universe. There's been, and maybe Ruth will show that later, there's been some remarkable developments in understanding what the universe is made out of, what are the constituents of the universe. And one of the things we know is that the universe is expanding, but this expansion is not slowing down as we would have expected from the fact that gravity is an attractive force. This expansion is actually accelerating. So sourcing the late time acceleration of the universe, we need to postulate the presence of dark energy. And the universe is actually made out of 70% of dark energy. That's in addition to the component of dark matter that we also know we need to postulate to explain some of the structure formation in the universe or some of the behavior of the galaxies or clusters of galaxies. And so what we are made out of, ordinary matter, atoms, even light, any standard model of particle physics, everything we know and everything we interact with non-gravitationally only represents 5% of the total energy content of the universe at the current time. So one of the big mysteries is trying to understand what dark energy is. It's one thing to give it a name, dark energy, and it's another thing to really try to understand how it comes about. What is it the manifestation of? So a few years ago, well, I guess 13 years ago, I was giving a lecture in a summer school. And at the time, I thought I will kind of classify, summarize the various types of models that people have come up with at that time in trying to understand what dark energy was. So this was the different directions people have been exploring at that time. And more recently, I thought it'd be appropriate to update these pictures. And so I included the various types of models that have been proposed in the literature in the past decade. And really, it's been completely exploding. And that's not even an exhaustive list of all the models that people have been exploring. These are a big class of them, but not all of them. And so really what I like to communicate is how much creativity there is in that field in trying to come up with reasonable models to explain the late time acceleration of the universe. So the issue is not at all a lack of creativity. In principle, we have beautiful models that could describe the late time acceleration of the universe in a way or another. But the issue right now is that there's such an explosion of creativity, which is a good thing, that we actually need to find some way to separate them out and single out some region in this landscape of models where we're more likely to be, which is more closely related to the nature of reality. And so there's many different ways to go about it, and many different type of criteria we can try to establish on ourselves, on the models that we have. So if we have a model, for instance, to describe dark energy, but it doesn't need to be dark energy per se, this is just a scientific question. If we have a model, the first diagnostic we can implement is simply at the theoretical level. Before we go out there and send some multi-million missions to compare it with the predictions of our model, we should really ask ourselves the question of whether or not a model makes sense. And this seems kind of an obvious question, but we have whole workshops and conferences really trying to address these questions. Sometimes these criteria are very subtle to diagnose. Sometimes a model may seem to make sense physically, but actually not as valid as we thought it was in the region where we want to use it for. Sometimes it manifests some type of instability, which only appear if we really push the model to its limit. So there's a whole consortium of various theoretical ideas or theoretical criteria that we can impose on a model to understand whether it makes sense theoretically in the first place before we can start using it and comparing with observations. So once we're convinced that our model makes sense, at the very least in a region where we want to use it for, we can then go and ask ourselves the question of how consistent it is with current known observational constraints. And there's a multitude of observational constraints, and it's very easy to fit one particular type of observations or one particular type of experiments. But nowadays, there's such a high class of various constraints on different scales, probing different aspects of various models, that really it requires a tremendous work to be able to see if a particular model is consistent with everything we know about the nature of reality right now. And this is particularly true with gravity, where we have such a plethora of observations on different scales. And then if we're convinced that in principle it could fit our observational data, and this is something hopefully Ruth will talk more about, then we can ask ourselves the further question on how significant it is for future observations, if it can lead to any signatures from the point of view observations or experimentals, so that it can potentially be rolled out in the future. Okay, so this is typically the way we go into constraining the models and then converging toward a model that makes more and more sense and seems to be more and more representative to reality. But all of these criteria are criteria that can be implemented directly at the level of the model itself, something that happens within our relatively low energy world that we live in, that we're experiencing. And we can ask ourselves some slightly different type of question, which is not about the model itself per se, but how it fits in a bigger picture with other models. And what I mean by that is trying to understand whether the picture we have in mind will ever have any chance of being embeddable in a standard high energy completion, in a fundamental completion of gravity and everything, which could potentially make sense. Even if we don't know what this fundamental completion is, there is some information we can gain from some criteria at high energy that are hidden at low energy, and extracting this information out from a low energy point of view really can allow us to put much more stringent constraints on our models at low energy and make progress. So it's very obscure at the moment. I'll hopefully by the end of today, it'll be much clearer. I'll try to explain what I mean by that. So the world we live in, even if we do LHC physics, whatever we do in the world today, is relatively low energy. It's all the way down to cosmological scales, which would be 10 to the minus 33 electron volt. Maybe we go all the way up to, let's say, 10 to the 12 electron volt, but it's relatively low energy compared to a fundamental theory of everything that may happen at high energy. And I certainly don't know what's going on at very high energy, at energy as high as the Planck scale or the string scale at a very high energy. I don't know what's going on there. It's really too hard for me to compute anything. But what I like at the very least is that whatever representation we have of our world at low energy, that it has any chance that it could in principle be implemented in a high energy realization that would make sense, even if I don't know what it is. I like this theory to be able to cascade at some point at high energy and maintain some physical behavior at high energy. So to be a little bit more concrete, you may have a model at low energy that describes the world and may seem consistent with it itself from the theoretical priors that we have. It may seem consistent in fitting with all observation and experiments. And now you can ask the question, what would happen for this model at high energy? How can I implement it within a high energy? And the surprise is that for some models, we know that there will be never any possible high energy implementation for those models. And it's not a lack of creativity in the type of models that we allow for ourselves at high energy. I'm not going to commit into having string theory. I'm not going to commit into having a particular field content. I don't know what's going on at high energy. There might be an infinite number tower of higher spin states or anything else that I can't even describe with my own words. I don't know what it is, but I know that such a model will never remain fine and physical at high energy. So it'll never enjoy a standard high energy completion. So the way we go into proving this type of statements is we start actually from the top and we cascade down to conditions that are going to be implemented at low energy from the requirement that what's going on at high energy is meaningful. So let's imagine we have some high energy completion. I can't describe it, but what I like to do is impose some natural properties of physics at high energy. One of those properties is that I just want the sum of probabilities to be equal to 1. I want this to be true also at high energy. It doesn't seem extravagant, so I'm going to ask myself that. I'm also going to ask myself that things remain causal, at high energy, so that I can't have a particle with sufficient high energy that goes and kill its grandfather and then violates causality at low energy as well. So this seems relatively natural properties. And those properties that we impose at high energy then manifest themselves as statements on our low energy descriptions of the world. And particularly, they manifest themselves on condition of the scattering amplitude at low energy. So I was actually quite excited to give a talk to a more mathematical audience, because typically I have to gloss over some of the mathematical details that the physicists don't want to talk about. But perhaps I need to explain a little bit more what I mean about scattering amplitude. I don't know how obvious all of this terminology is to everybody. So just to be on the same footing, what I mean by a scattering amplitude, let's start with an initial state. Let's start with a particular, even if you don't like the terminology initial state, let's start with some basis, and I define a time evolution, and I want to see how this state evolves in time. And so the process of the evolution is captured by the scattering matrix. So if we have a state at a given t's minus infinity time, we want to see how it will have evolved and potentially interacted with other things and ended up in a final state at t's plus infinity. And this is described by a scattering matrix. And once we have the scattering matrix, we can define a probability for an income state, initial state at t's minus infinity, to evolve into an outgoing state, final at t's plus infinity. And so we'll define the probability to go from the initial state to the final state as this kind of inner product of the initial and final state in the weight of the scattering matrix. And one of the properties of this scattering process is that we like the probability to be positive. So that seems kind of a reasonable assumption, and it doesn't rely on any knowledge about what's going on with the physics. This is, I would say, a pure mathematical statement if our Hilbert space is a complete. Oh, well, actually here, always. Okay. Now, one of the first requirement I'm going to impose on myself that I like physics to satisfy, both at low energy and at high energy, is that of unitarity. So what it means is that if a law exists on how to go forward, then we should be able to find a reverse law. And that implies that the scattering matrix, I can define its dagger, and if I put them together, that should define the identity. So the scattering matrix should be a unitary operator. And so that also means that if we sum up all the probabilities, the outcome of the sum of all the probabilities should be equal to 1. And that's really just saying that if I choose a complete Hilbert space, or if I choose a Hilbert space with a complete basis of states, K, I should end up with a identity in terms of the sum of all the probabilities. Now, what we do typically is we separate out the trivial part of the scattering process with the interaction part of the scattering process, really where the physics comes in. For an interacting theory, we can define the transition matrix, which is the scattering part, the scattering matrix minus the identity, because this is just the trivial part. But now requiring that the scattering matrix is a unitary operator then implies that the imaginary part of the transition matrix is equal to the same relation T dagger T, which itself has to be positive. And so if we write this in terms of the scattering amplitude, which I'll be discussing about, this is typically more the concept we use, which is related to the elements of the matrix with the transition. And I remove out all of the delta function related to conservation of momentum. Here, if we're in 4-dimension, the 4 momentum. So this is simply the scattering amplitude, and then apply what this condition implies on the scattering amplitude. It tells me that the imaginary part of the amplitude has to be positive. So this is simply a statement that comes out from unitarity. If you want unitarity, then the imaginary part of the amplitude in the real energy axis has to be positive. Okay, so this is one requirement that are like physics to maintain, no matter what energy scale, including at infinite high energy scale. Now, another requirement that I like to impose on myself is that of causality. So we all have some understanding of what causality is. In principle, it means that if I have a system and I kick it, I want this system to respond after I kicked it and not before I kicked it. If we start responding before I kicked it, then I would have a violation of causality. So this is something quite standard in the way we're thinking about, but we're just going to want to phrase that in a more mathematical statement. So if that means that if I have a system and impose a source on the system, I kick it in a way and another, I want the response to start after the source started in and not before. And so the response must have some type of theta function built into itself for this behavior to happen. So to be a little bit more concrete, for any system, I can define a retarded propagator. This is intrinsic to the system itself, so that for whatever source I decide to impose on the system, I'll have a response which knows about its own intrinsic retarded propagator and whatever source we impose on it. But in order for any source that we have for the response to start after the source, we need to have that the retarded propagator vanishes for negative argument. So the requirement of causality tells us that the retarded propagator has to be 0 for negative t, which is again what we expected, and we have to have a theta function built in. Now, if I go into Fourier space and build up my retarded propagator in Fourier space, what I would typically have is that the value of this retarded propagator is equal to the residues of the present in the upper half of the complex plane of the Fourier transform of the retarded propagator for t is negative. So for t is negative, I need to deform my contour by the upper half of the complex plane, and I pick up all the poles that are present in the upper half of the complex plane. And so if I want to impose causality, I need to have that the Fourier transform of the retarded propagator has to be analytic in the upper half of the complex plane. I'm not allowing myself any non-analytic structure of the propagator in the upper half of the complex energy plane. So this is where the notion of causality is directly related to that of analyticity. Now, this was the case for the retarded propagator, but we can go through exactly the same argument to show that the same thing goes through for the scattering amplitude. So we can take a process at low energy, let's say, and we can compute the scattering amplitude. It's convenient in the case of scattering amplitude to depict things in terms of not just the center of mass energy, but really the center of mass energy square. This is just for pragmatic reasons. And we can define it in the complex center of mass energy square. Now, the notion of causality, as I mentioned before, in terms of the retarded propagator, was that it was analytic in the upper half of the complex plane. Now, for the scattering amplitude in a complex energy square plane, that will correspond to the amplitude being analytic in the whole of the first Riemann sheet of the complex plane, at the exception of potential poles and branch cuts on the real axis, but just on the real axis and not anywhere else in the complex structure of the first Riemann sheet. Okay, so now let's imagine I have a model at low energy. I'm going to call it a low energy effective theory at low energy. And I can compute some scattering amplitude at low energy, and I can trust it so long as my theory remains valid. For any theory at low energy, it will always have a finite regime of validity where I can compute things and I can trust what it is I can compute and compare with the real world, comparing it, for instance, with LHC experiments or something like that. So it has a finite region of validity. Now, when we're outside this region of validity for my low energy effective model, I can still define an amplitude. The amplitude is well defined there. The only thing is I can't use my low energy model to compute it. I need to introduce new physics in the game. I need to understand what the realization of what's going on at high energy is for me to be able to precisely compute the amplitude. But the amplitude is still defined there. And there may be an infinite number of layers of physics that may need to come in all the way up to a high energy fundamental completion of gravity and everything, ultra high energy. This may be at the Planck scale or slightly lower, I don't know, but there may be a lot of physics going on there. And I certainly can't use my low energy effective field theory to describe the amplitude at high energy or in any regime here. However, it still seems appropriate and reasonable to expect the amplitude to remain unitary all the way up to high energy, because after all, you still expect the sum of probabilities to sum up to 1. That doesn't seem extravagant. And then we're still going to require some level of locality. We're going to expect physics to remain sufficiently local so that we can define the amplitude at high energy and its Fourier transform as well. And then if I further ask or require the notion of causality, this is what manifests itself under the statement of causality, now in the whole of the complex plane. And it is a statement of analyticity that precisely link the other assumptions of what we have at high energy on the amplitude, for instance, unitarity, to some behavior of the amplitude at low energy. And this connection, you can't see it from the low energy effective field point of view by itself. You wouldn't have been able to establish these criteria at low energy by themselves. It's really this communication through the means of analyticity that allows you to make the connection between high energy and low energy. So let me be a little bit more precise on how we can make this connection if you're interested. Let me imagine that I have a UV, a high energy completion, which is unitary in the sense that the imaginary part of the amplitude is positive in the real axis here. And if I also assume Lorentz invariance, it tells me that some processes that happens in some direction, the amplitude will be the same as if I revert some of the time and space direction. And so that's related to crossing symmetry. In a sense, it tells me that the imaginary part of the amplitude also has to be positive in this region. And now if I further assume causality at all energies, that is embedded under the statement of analyticity and allows me to derive an expression for the derivatives of the amplitude at low energy and relate it with a Cauchy integration formula along the real axis and in some arc at large energy, plus the poles that I can subtract because they are within the regime of validity of the FT. Now, if we further assume locality, which manifests itself as a statement, what we call the Froissart band, or in other words, we want the amplitude not to grow too fast. The amplitude at large energy can grow, but we don't want it to grow too fast so as that we can't define a Fourier transform anymore. So we want some level of locality. If we want to impose saturation on how fast the amplitude can grow, then the arc at infinity, the arc, I can send it to infinity and its contribution will vanish. And so then we have a direct relation between the derivatives of the amplitude at low energy, which we can compute within the regime of validity of the model, and an integration over the branch cut over the imaginary part of the amplitude, which is positive. And so it tells us unitarity at high energy implemented with locality and causality tells us that some derivatives of the amplitude at low energy has to remain positive. And if you have a model which seems to be completely consistent, but this condition is not satisfied, then this model could never be implemented into a standard high energy completion that would satisfy this requirement. So maybe causality would be violated, or maybe unitarity would be violated. Okay, so this is the essence of those positivity bounds, which are applicable already at low energy. Now, this seems maybe a little bit abstract, but it's something we're actually using, whether we know it or not, but almost on a daily basis. So one of the examples of that is, let's imagine I have some glass, I have some water. Let me take a droplet of water, for instance, and I shine light through it. Then I know that for relatively low frequency light, the light will start interfering with the molecules of the water, and that would slow down the propagation of light through this medium. Whereas if you shine light with a very high frequency, then it's going to be completely unaffected by the presence of the water, whatever medium you have there. And so the speed of light at high frequency as it goes through a medium isn't affected by this medium. It goes back to the same speed as if you were in the vacuum. And this is really the essence of a prism, that the speed of propagation in a medium for light depends on the frequency of the signal. Now, the reason I'm talking about that is because the connection between how light interacts with the medium is through the refractive index, which is precisely related to the scattering amplitude. You can really draw a direct analogy with that. And so we define the speed of light through a medium is determined in terms of the refracting index in that sort. But this refracting index itself is related to sort of a scattering amplitude between the photon and this medium. So it could be water or whatever you have in there. Now we can apply exactly the same criteria. It's exactly the same. It's a slightly different language, but it's exactly the same idea. Using unitarity that tells you that the imaginary part of this refractive index has to be positive for all omega, up to infinite omega. And then asking for causality, which demands the notion of analyticity, that is what allows you to relate the refractive index at zero frequency or at very small frequency with that at very high frequency through these Kramers-Kronig relations. And because of unitarity, this integral has to be positive. And so it's directly this requirement of causality but implemented with that of unitarity that tells you that the speed of light at low frequency, even when it travels through a medium, should be smaller than the speed of light at higher frequency, including the speed of light at infinite frequency, which is the front velocity, which is the speed of propagation of information. And it is that speed that has to be luminal, exactly luminal. Anything else has to be subluminal, not only because of causality, but also because of unitarity. So this seems to be a requirement that we're very used to in our everyday life, and we always implement, but it's worth keeping in mind that this requirement of subluminality at low energy is only related to causality through these positivity bounds, and only related to causality if we also implement it with unitarity, locality, and some notion of Lorentzian lines. So that's one thing. And in addition to the notion of subluminality for non-gravitational effective field theory, we have, in any effective field theory, we have an infinite number of other constraints. That of subluminality is the simplest to picture in physical terms, but there's an infinite number of other constraints, which I wouldn't have heard of before I started working on that. But just to give you an example, just to be pragmatic on how we can use this type of constraints, and let me just imagine, not for dark energy for a second, but just for the standard model of particle physics. Let me just imagine I have my standard model of particle physics, where the fields also have a particle analog, and at the moment, this completely represents everything we know about all the interactions of nature aside from the graviton. So let me not put the graviton here. Sorry about that. Okay, so since new physics hasn't been discovered at the LHC yet, maybe there's some signs of it or not, I don't know. I can remain agnostic about that as well. But one procedure that particle physicists do is to implement the standard model of particle physics with potential corrections that will manifest themselves at high energy. So it's an effective field theory approach for physics beyond the standard model. Some examples of operators or corrections that come in beyond the standard models are written here. For this level, they're not too important what they are. This is the type of operators that people consider. In particular, for the W boson, they consider some dimension 6 and dimension 8 operators. The dimension 6 operators are not very important, and the dimension 8 actually can be constrained with current experiments. And in order to remain, this is in the phase space of these parameters for the corrections of physics beyond the standard model. Current experiments tells you that you should be within this region of parameter space, within that region of parameter space. Now, from the point of view of the low energy effective field theory, there's nothing wrong being, for instance, in this point or in this point or in this point of parameter space. Everything seems stable, completely consistent, everything seems fine. But requiring these positivity bounds, implementing the positivity bounds I mentioned before, so requiring that the high energy completion is a sensible one in the sense that it's unitary and causal, dictates that you have to be in the green region of parameter space. And this is something we would never have anticipated if we were just focusing on simple low energy requirements. It is really requiring some communication on what was going on at high energy. So this is just an illustrative point on how complementary these theoretical priors from the high energy completion are with respect to experimental bounds. And so putting them together, you can really converge much faster into understanding where we are in parameter space or where we are in the models that we are exploring. Okay, so all of that so far was within the context of non-gravitational effective field theories. Now, as soon as you like to add gravity, like always for everything, things become much more subtle, sometimes to the point that all hell breaks loose. So there are many reasons why some of these conditions, particularly that of locality, may be a little bit more subtle already at high energy. But if I take string theory, it does satisfy the same level of locality, particularly the Froissart band, as I like to impose on myself. So I think it is reasonable to maintain these conditions at high energy. Depending on the audience, I speak with, not everybody agrees with that, but for now, let me assume I still maintain locality, and hopefully no one disagrees with the notion of causality, for instance, that we're imposing at high energy. Now, even imposing the same conditions at high energy, the way those conditions manifest themselves as bounds on the amplitude at low energy are more subtle. And then how those bounds manifest as constraints at low energy in terms of subliminality or the constraints is also more subtle. The reason it's more subtle is because in the way I described how to use the notion of causality through analyticity before, we performed some Cauchy integration formula where we had some mass gap here, or some region in the real axis, which was analytic. And so we could perform some Cauchy integration or continuation between the upper half of the complex plane and the lower half of the complex plane. Now, as soon as we add in gravity in the game, actually the branch cut goes all the way down to the mass of the graviton, which is 0. And so technically there's no room for analyticity. And so we can't really use the same formula in precisely the same way because the level of analyticity just on the real axis is no longer the case. And this may seem the same thing for any massless particle, but it's particularly the case for the graviton because it has spin 2, and so the amplitude itself grows sufficiently that it is an issue for the lack of analyticity at that point. So another way to say that is that as soon as we have gravity in the game, and you want to compute some scattering amplitude, it doesn't matter even that you want to compute anything related to gravity per se. Let me just compute some scattering amplitude between photon and matter. And a priori, I'm not interested in gravity at all, but just the fact that we allow gravity to play with us, then gravity is going to come and spoil everything, because you can't prevent from having a graviton exchange that we have photons interacting with gravity or graviton, and then the graviton decay into photon. These things can happen. And the very fact that you have a graviton exchange affects the analyticity structure of the amplitude and spoils this type of requirement positivity bounds that we had imposed on ourselves before. So with gravity, the positivity bounds just becomes approximate. They're not strict bounds anymore. And all we know is that in principle, it could be a little bit negative. Those derivatives of the amplitude could be a little bit negative, but not too much, so that in the limit where you switch gravity off and you send G Newton to 0, which means you send the Planck scale to infinity, this contribution decay away. But in principle, you could have something negative in those contribution of the positivity bounds. So with that in mind, since it's not as rigid as we had in non-gravitational theories, but since in non-gravitational theories, we had already established a link between positivity bounds and the speed of the field at low energy, maybe one outcome, one possible route to take is to shortcut these positivity bounds altogether and go straight for the speed and just say, let me use the speed as an indicator on whether a theory is meaningful or not at low energy, because there seemed to have been a connection before. So let's imagine now, let me go into the real gravitational framework, and let me imagine that we have some curved geometry. You can be around a black hole. This doesn't need to be a black hole. You can have a star in the middle or whatever you want. And let me look at the propagation of, for instance, gravitational waves on that geometry. So let me do that. In principle, this is what I would have if I were in a pure theory of GR, not interacting with anyone else. This is the trajectory I would have. But as soon as the graviton is allowed to interact with other things, as it will always do, you can't prevent it from creating pairs of virtual particles. And through those pairs of virtual particles, the gravitational waves will effectively feel the trajectory about their geometry. And this will affect the propagation of the gravitational waves through the interactions with other fields on a curved geometry, so on a curved background. And the outcome is that the speed of low frequency gravitational waves is no longer luminal on curved backgrounds. It will start deviating from luminality. There's some correction that depend on the curvature themselves, and then also on the type of field that it's allowed to interact with. So this field can be whatever you want. It can be the Higgs boson, it can be electrons, it can be neutrinos, whatever you want. It would in principle interact with everything else. Every single one of those fields will lead to a small departure of the speed of gravitational waves on curved backgrounds by an amount of this form, where m here is the mass of the field you're considering, and alpha is related to the interaction between this field and gravity, and related, for instance, to the spin of this field. So it's intrinsic to those fields themselves. Okay, so now that we know that the speed of gravitational waves in principle is not one, and that's kind of similar to having light shining through water, for instance, but now it's through the interactions with all the other fields of nature, and because of the presence of curvature. As soon as you know that, you may ask yourself whether one way forward is instead to start constraining our model based on the speed of those gravitational waves. And if some models invokes the presence of some fields, I don't know, some dark energy field, for instance, that would always lead to a particular way in which they correct the speed of gravitational waves, then you may want to ensure that the way they affect the speed of gravitational waves is so that it's always subluminal. So if I had more time, but I don't think I have so much more time, sometimes I put that to the vote and see what people think about this strategy, because that seems quite good to me. So if I was sane, which I'm not, if I was sane, I would say, yeah, let's do that. I mean, that seems like the best thing to do, because it's well known that as soon as you have superluminality, then it's related to a causality. And so if you don't want a causality, you may not want any notion of superluminality. So we should put constraints on the type of interactions you can have between gravity and any other field that exists in nature, so as to ensure that in any possible situation, you always lead to subluminal speed. That seems like a good strategy, except the connection between superluminality and causality violation is actually only present through positivity constraints. And if you also implement unitarity and these type of things. And we already said that the positivity constraints are not strictly true in the presence of gravity. And so you don't expect actually the requirement of superluminality to be strictly related to that of causality violation. So I'll try to convince you of that in the next few minutes that I have. But before I try to convince you of this, let me go into this first part of the sane part of the picture in describing why, generically, any violation of superluminality, any amount of superluminality is directly related to causality violation. So let's imagine you have a configuration where you had some miraculous fluid, let's say dark energy or whatever, some miraculous fluid, where you can shine gravitational waves or light or whatever you want through it, and they become superluminal. Some of them are superluminal. So let's say some low frequency light is superluminal through here, or gravitational waves. And high frequency is strictly luminal. It follows the standard geodesic, the sun path. Now you can have a superluminal trajectory in the medium, and then when you come out of the medium, then you have your standard luminal trajectory as you had before. But that allows you to have some element of what I'll call support outside the standard light cone that you started with. But you start with Minkowski to some extent in here, and particularly at past infinity and asymptotic space. And you end up with Minkowski here as well, where you do have Lorentz invariance in here, you do have Lorentz invariance in there. The only reason you're not having Lorentz invariance in here is because you have a spontaneous breaking of it due to the fluid being present. But otherwise, at future infinity and past infinity and the asymptotic configuration, you always have Lorentz invariance. So as soon as you have a little bit of superluminality, it doesn't matter how much you have, you're allowing yourself to having some support outside the light cone. So that means that, let me imagine here, I set my origin around the point of person A, let me say, at that event there, and I define her light cone like so. So if she sends light, it will go through the light cone, through the null direction, and then any massive particle will travel inside the light cone. But if I'm allowing myself for superluminal propagation, even a tiny bit of it, then in principle, she can send a signal that affects the event at B. So A can affect B. Now, as soon as I have that, and I believe in Lorentz invariance as a fundamental symmetry, then observers which are boosted with respect to each other should be equivalent. And so I can allow myself to boost into a new notion of time, T prime, and that changes my notion of space as well, X prime. If I move with respect to A, that's my new notion of time and space. And for that boosted observer, the point B is located in the past of point A. So as soon as you have superluminality, you can have that your future affects your past. And that is, by definition, some notion of causality. So this is why, even if you have the tiniest amount of superluminality, you can always then engineer a configuration so as to surf on as much of it as possible and have as large a support outside the light cone as you want, and then build up a time machine if you wanted to. But that's in the absolute without gravity. In practice, when you're dealing with gravity, as soon as you have stuff present in your space-time, you can't prevent it from creating curvature. And this curvature is precisely what's going to tell you that you cannot surf on as much superluminality as you want to. There's a finite amount you can do it. One way to see that is in the context of the black hole configuration we had before, where I imagine a send to signal, one which is would travel one which travels at the normal speed of light, and one which travels superluminally. But in the configuration we're considering, the superluminality is only present due to the curvature of space-time. It was going like the curvature of space-time. And so there's only really a finite region of this configuration where you are surfing on superluminality. The curvature at asymptotic infinity here and there vanishes, and therefore there's no superluminality here, there's no superluminality there, there's just an amount which is present there. But you can never engineer a configuration so that you can have as much element of superluminality or as much support outside the light cone as you want to. So if you wanted to have more and more support outside the light cone, you would like your curvature to become bigger and bigger. But in this configuration, if you want to have the curvature becoming bigger and bigger, you're going to get closer and closer to the black hole, and there'll be a limit to it. So you can't do that at will. There's a limit to it. Similarly, if you're trying to send a signal with as high frequency or energy as you want to from infinity, there will be a finite distance from the black hole. You have to remain away from it so that you can still use your low energy effective field theory and remain within its region of validity. If you send too high energy signal too close to the black hole, things are going to be, the operators you're using are become too large, and you're going to go outside the regime of validity of your effective field theory. So in the gravitational setup, it is always the case, and this is really just a hand wavy argument. I can make that more precise, and I can discuss about that more if you wanted to later. But in the gravitational setup, it is always the case that if you are having superluminality related to the curvature of the space-time due to the interaction between gravity and other fields on the curvature of space-time, the amount of support that you can allow for yourself in those configurations is always going to be smaller than the inverse of the energy or the wavelength of the signal that you sent in. And that means that it's not resolvable. Unlike in the case without gravity, where you could have some support outside the light cone, which could be in principle as large as you wanted to, there's no limit to that. As soon as you're dealing with the gravitational setup, then there's always going to be a finite amount of curvature you can deal with, a finite integration of your superluminality that you can deal with. And that always leads to a support outside the light cone, which is smaller than the wavelength of the wave you started with. But if you start with a support outside the light cone, which is smaller than even the wave that you're sending in, then it's not meaningful to consider just a point-like approximation and trust this quantity. You really should think of sending in a wave packet and understand how it gets delocalized or something like that. But what it really tells you in there is that things remain under control, the secular effects remain under control, and this amount of superluminality that you're having is not resolvable, is not physical in some sense. And so the amount of superluminality is so small that you can never build it to lead to any violation of causality. And so that's relevant for putting constraints in all sorts of models that we're using for ourselves in describing the world of cosmology, whether it is for the cosmological setup when we're trying to understand how dark energy evolves, and some models of dark energy may lead to a speed of gravitational waves which would otherwise qualify as being superluminal. It's also relevant when dealing with what's going on for black hole. Around black holes more and more, people are exploring what are the corrections from various fields being present on the waveform of gravitational waves through the events of black hole mergers or this type of situations. And typically the approach that has been used so far, and that I used before a few years ago, was to compute the speed, and as soon as you led with a speed which is superluminal, to segregate against those models. But actually the level of superluminality is never connected with that of causality. And that is consistent with the fact that the positivity bounds, which is really how we get this notion of causality being communicated into the notion of subluminality, this is manifested through the positivity bounds in non-gravitational effective field theories. But as soon as gravity is in the game, even if you're not interested in gravitational waves per se, as soon as gravity is in the game, then you only have approximate positivity bounds, which tells you that the speed can be a little bit superluminal by an amount which is suppressed by the Planck scale. And so I think there's a comment there. And let me stop here. Just to finish, let me show you an example of bounds that we can put on our low energy effective field theories, going back to the example of dark energy. So this is some work with this amazing gentleman, Scott Melville and Johannes Noller, where we can take a particular model of dark energy. This is called Quartic-Herndesky, doesn't matter too much. It has some parameters, CB, CM, CT. And in yellow are the constraints from observations that you put on those type of model of dark energy. So from the cosmic microwave background and this type of requirements. Now, if you were just putting constraints from the low energy effective field point of view, and asking, for instance, for subluminality, you constrain yourself to be in the purple region of parameter space. But what I'm advocating is that the constraints from causality is not always demanding subluminality at low energy. Sometimes you can have superluminality at low energy, and that's not constrained with causality violation. What you have to impose on yourself is this requirement, and let it be what you want. And when you do that, the notion of causality and those positivity conditions end up on being in the black region, which is significantly away from what you would otherwise have expected. So I'll stop here and just summarize that there's some level of analyticity in the sky that we can actually go for. that manifests itself through the positivity bounds, which can be applied on low energy models, so as to probe whether they could enjoy standard high energy completion. And they demand, those positivity bounds demand some notion of unitarity and causality, which manifests itself through unitarity. So I've shown you various examples where we can use them to complement observations, but most of what I wanted to talk about is the connection between that and the notion of speed at low energy. And in particular, while in the non-gravitational setup, there's always a connection between superluminarity and causality violation. In the gravitational setup, due to the approximate positivity bounds, the connection between superluminarity and violation causality is more subtle, and you can have situations where you can allow for yourself a small amount of superluminarity and not be in tension with causality. So I'll stop here. Thank you.
Great. If we can just thank the speaker first, and then we'll take some questions. So there's a question already in the chat. I think you noticed that, Claudia.
Yes, I didn't know if it was someone telling me that I had to hurry.
No. So I'll just read that out. So general relativity is not a causal theory because it allows closed time-like curves, for example, near the ring singularity of a cursed black hole, which can be naked. How does this affect the discourse on causality? And that's from Konstantinos Dimopoulos.
Yeah, so I wouldn't agree with that. I mean, I think that's part of Hawking chronology protection mechanism, where you can't trust general relativity close enough to this configuration. So if you go too close to the configuration where you would end up having some causality and thinking you can create a closed time-like curve, then you are going outside the regime of validity of that model.
Thanks. And just to clarify, if people could put their questions into the chat, that makes it easier for me so that I don't have to flit always through to look for people's hands. So a question from Robert McKay. Does there have to be a physical form of dark energy rather than just cosmological constant?
So you can absolutely have a cosmological constant. That's absolutely the most natural realization of dark energy. The main reason why people are exploring alternatives is the cosmological constant has the cosmological constant problem, that its order of magnitude is 120 orders away from what we expected. And so it makes us very uncomfortable to just stipulate a cosmological constant when you expect quantum corrections from any field that exists in nature to destabilize the value of this cosmological constant. So in actually, I can show you that in, let me go back. Am I still sharing? What am I sharing?
Yeah, you're sharing. That's right.
Are you seeing the summary now?
We can see the summary. So if you click, then we'll be able to see.
Okay. So you can have a cosmological constant. One of the issue with the cosmological constant is its order of magnitude. And so a lot of what people are trying to understand is whether maybe there's a landscape of vacua and whether we happen to be in a particular vacuum for some entropic reasons or some entropic reasons, or whether we've been able to dynamically tunnel from one another. In a lot of the models that have been considered in here, and some of the others that have been considered in there, actually you do take a cosmological constant as being fundamentally the source of the late time acceleration of the universe. And what you're trying to do through this additional physics is to explain to explain a relaxation mechanism as to why we're observing such a small cosmological constant when the quantum corrections to it are expected to be so large.
Thanks. Then there's a follow-up question. Does the causality discussion need an absolute time and stationarity?
No, it doesn't need stationarity. No. So, for instance, I'm applying that to the cosmology setup. I haven't gone through the details there, but you can do that through the cosmology setup here. and if you're interested, I can go through the details of how you can see the same level of discussion going on in there. So it's definitely not stationary. You are in an evolving universe. So all you need to do is now simply think of what you mean by the physical distances at a particular time. So any time evolution will allow it to put that into the discussion. So you wanted stationarity and an absolute time. I mean, again, no. The end of the result is that what you end up with is this supporter satellite cone over the wavelength itself is much smaller than 1, and that by itself you can relate it to a scalar quantity. So that's going to be the case in any setup at the end of the day, and that's completely independent of how you choose your time and what particular configuration and what particular symmetry you're dealing with. In the end, you're having just a scalar quantity that always ends up being 1, much more smaller than 1, and that's all that matters for the notion of unresolvability.
Okay, and then on a different perspective from Gleb Grebetkin asks that when we go from classical to quantum mechanics, we have to completely change the nature of the mathematics that we're using to describe phenomena. And they ask, is it possible that we, again, are going to have to change to a completely different concept of maths to really understand what's going in the high energy limit? And I guess I would modify and say, do you feel that we've already done that? And if so, what is the difference between the maths that we are using for high energy limit and that we're using at lower energies?
Yes, so that's definitely true that at low energy we are comfortable talking about. Let me even see. I don't know where I want to put it. Let me go in that picture. At low energy, we're comfortable talking about fields in a particular local setup, and all of that we know is going to get modified at high energy. And so that's why we're really focusing on a notion of amplitude, which we can still use as a concept at high energy. But it's true that some of the other concepts that we use, for instance, that of locality, we're going to need to modify as we go to high energy. That's definitely true. But we have already made a jump. I mean, we know that however we like to describe the physics at low energy, we're not, and the math we're using to describing it at low energy, we're not allowing ourselves to use exactly the same language at high energy, neither the same mathematical nor the same physical language at high energy.
While we're on this slide, Claudia, I have what is an embarrassingly stupid question just about notation. So you're using this del notation?
Yes.
And you were talking about analyticity as well. No, I mean, when I think about analyticity, I think of del bar equals 0, right? The del bar operator is
sorry.
Right, so I was a little bit confused what your del operator is here.
Sorry, I can tell you why I did that. Typically, we're not working in these variables. We work in Mandel-Stern variable, and I didn't want to add another layer of topology. So it's just the second derivative with respect to omega squared. This is
okay, right. I was like, what? How does that really? Okay, and then sorry, when I think about, for instance, work that goes on in spectral theory,
yes.
I'm thinking about what you're talking about here is that if you make this implication of analyticity, then if you know what things are on a dense, on a convergent sequence within any part of it, you actually, unique analytic continuation tells you what it has to be everywhere else. Is that part of what's going on here? Is that sort of the concept?
Yeah, so I can show you exactly. Well, really, the concept here, that is the concept, yeah. The only thing is we know the amplitude here up to some corrections.
Yeah, that's the point. Of course, that there's the devil's in the detail of those corrections, right? So analytic continuation doesn't necessarily tell you as much about if you only know it to approximation. Yeah. Okay.
You know exactly what's going on here as a Taylor expansion but you can only trust her to a given order.
Got it.
Yeah. So it's really in making that step here. It's not a trivial statement because we don't know what's going on. Yeah.
Yeah. I figured. Okay. There's another follow-up question from Kostas, who asks, what about the Gödel universe, which violates chronology throughout the entire space-time, and is an exact solution to Einstein equations?
Yeah, I don't know then. I don't know. We have to discuss about it. I mean, if you have a specific example that doesn't go under Hawking chronology principle, we can definitely talk about it. On top of my mind, I don't know what it is.
Okay, well, obviously, plenty of examples to still go through. I don't see any. Are there any further questions before we wrap up?
Yeah, I mean, Kostas, I'm happy to discuss about that. I mean, my feeling is that there must be a resolution, but I can't tell you what it is for that. But the Hawking chronology protection is very strong typically. It's almost so strong that in the end, when you implement it, it becomes a tautology. As soon as you want to go to construct to boost yourself so as to go backwards in time, then the back reaction is going to be infinite.
Hello, Claudia. This Gödel universe is actually quite famous because it violates chronology throughout space-time, as I said. It's a homogeneous solution with rotating dust and a cosmological constant. When Gödel was a friend of Einstein, when he presented it to Einstein, he was furious, but he couldn't disprove it. Yes, so it's quite famous.
Yeah, I thought you could say was a friend of Einstein until he presented that to him.
Yes, probably.
Yeah, if Einstein couldn't disprove him, I'm not gonna say.
All right. Well, Claudia, this has been fantastic. And I have to say that I've never imagined that I possibly could have a glimmer of understanding about these fantastic topics. And you've really, boy, but do I feel, I mean, I at least have the delusion of understanding something now, which is very gratifying. So thank you so much for your talk. If we could just have another round of virtual applause, or, you know, turn off your mute and we can actually applause. Anyway, thank you so much. And I regret that one of the consequences of online meetings is that occasionally the technology does not succeed. And unfortunately, we've had such a problem with our second speaker, who we've not been able to connect to, which is a great sadness to us, as I was really looking forward to her talk as well. So I'm very sorry to say that unfortunately we won't have the second talk. That's the conclusion of the talks, and I will pass back over to Kathy to close. Kathy? Maybe I'll put, okay, so maybe we've also had a oh, Robert's holding up a book about the cosmic microwave background. Who's that by, Robert?
Yeah, this is by Ruth Dura, and it's the second edition of her book.
Excellent. Good. Well, we don't unfortunately have the speaker, but we do have
reading in place.
Recommended reading. Fantastic. Thank you, Robert. That's nice to at least give us, is there a photo of the author?
Quite likely. No, I'm afraid not.
All right. Well, that's not so important as the photo of the title. So please do, everyone, have a read of the cosmic microwave background, a little light nighttime reading. As I said, I really apologize that we've not been able to reach the second speaker. So it's really a pity. We'll have to try to get her in for another talk at another time. And I also, it looks to me like Kathy has also been dropped. So
Kathy said that her Zoom was unstable, so she's probably got kicked off.
Okay. I think there is some formal sort of words I'm supposed to say at the end of the meeting, but I don't know the magic formula. So I'm just going to have to hope that that we haven't violated any physical laws in ending this meeting without the correct formula. But thank you again, everybody, for coming, and particularly to Claudia for that fantastic talk.
Thank you.